Hello and welcome to this practical training session for the Copernicus Marine Service Workshop MarineData4Africa. My name is Ergane and I will be your trainer for this session. So this Python training session for this workshop consists of 4 Jupyter notebooks, 1 introduction and then 3 exercises. This video is about the second notebook. So the first exercise, in which you will learn about the upwelling phenomenon in Northwest Africa. Before we start, these are Jupyter notebooks, so they consist of both text and code, Python code cells. And to run a cell, you have to click on the arrow on the top menu here, or you can also use the keyboard shortcut Shift and Enter. So we're going to talk about upwellings. Upwellings are ocean phenomena that occur along many coasts in the world, and they happen when the offshore winds chase away the water from the ocean surface so that the water from the deep ocean rises up to take its place. The water from the deep ocean is colder than the surface water, and also these water are very rich in nutrients, and therefore when the water rises up to the surface, it brings the nutrients, and because these nutrients are the very base of the food chain. They feed the phytoplankton, which then feed the zooplankton, and this zooplankton then feeds little fish, etc. And therefore the regions where upwellings occur are usually regions with very intense fishing activities. In this exercise we're going to study the northwest African coast, especially the Mauritanian coast, because this is this is an intense upwelling region. And we are going to study this phenomenon in this region thanks to the products from the Copernicus Marine Service catalog, so model and observation products. So about the data that we're going to use and the parameters, we are going to use both physical and biogeochemical parameters. So first, the wind, as we have seen that the winds generate the upwellings by chasing away the water from the ocean surface. Then we're going to study the temperature, because we have seen that the water coming up to the surface is colder because it comes from the deep ocean. We're going to study also the nitrate, as this is one of the nutrients that rises up to the surface. And finally, we're going to study the chlorophyll, because we're going to use this parameter to estimate the amount of phytoplankton, as phytoplankton use chlorophyll to carry out photosynthesis. So these are the parameters that we're going to use, and we are going to subset these parameters over the following region and time period. So the coordinates of the region studied are defined here. We are going to use the depth from 0 to 100 meters, and for the period studied, we are going to take from May 2021 to June 2021. And so this is the extent of the region we are going to study. So about the wind, we are going to study this parameter from the global observation product. For each of the model I'm going to present here, you will find the link to its web page, as well as the documents that describe the product and its quality. Here you can find a small description, and if you click on the link to access the web page here, you will access the Copernicus Marine Service catalog, and then you will be able to download the data. So for the wind observation, we are going to use the variables wind speed and northward and eastward wind to, well, these variables are used to study the wind direction. We're also going to use the physical model to study, the temperature. Again, you can find the web page and the documents about the product. And finally, our last product is the biogeochemical model. And in this model, we're going to use the variables the chlorophyll and the nitrate. Again, as for the other models, you can find its web page and its documents. All the products that I've mentioned before, they have already been downloaded and they are available here in the data folder. But if you want to download some data by yourself, for example, to study another region or another period, you can have a look at the introduction notebook. It explains the different ways to download the data from the Copernicus Marine Service. And this introduction notebook also shows how NetCDF files are constructed and how you can handle them in Python. So if you don't know well the NetCDF files and how to manage them within Python, you may need to have a look at this notebook before going through this exercise. So now that we have seen the data that we're going to use, we can begin our study. So this Jupyter notebook is a Python code, and the first step of such code is to import the necessary tools. So these are the libraries. Well, here are the libraries that we're going to use. They're NumPy, Xarray, Matplotlib, and Cartopy. Here you can find the links that describe better the libraries. And so here we're going to run the cells to import the library. The next step of this study is to load the products, and therefore we define the paths to the NetCDF files so that the code knows where to take the data. So we are taking here the physical model, the biogeochemical model, and finally the wind observations. So these are our three variables. We open the NetCDF files and we store the data into these variables. If you want to have a look at the product dimension or variable names, you just have to put the name of your variable into a cell and run it. And here you'll find its dimensions. So here depth, latitude, longitude, and time, as well as its coordinates and its variables. And here, for example, if you want to see what this variable is about, you can click here on the show hide attributes, and you'll see that this variable is the temperature and that its units are Celsius degrees. So that's it for the data. We are going to begin to analyze the upwelling, and the first step of this section will be to plot the evolution of the wind. So this is the map that we're going to generate, and before analyzing these results, I'm going to explain you how we built this map. So we can see on this map that we have in the background the wind speed. We also have the arrows that describe the wind direction. We have a landmass here. We have a coastline. On the top of the maps, we have the date, and we have one map for each date, and here one map refers to one day. So let's see how we constructed this figure. The first step is to define the figure and its size. Then we adjust the space between the subplot, so that this line adjusts here, adjusts the space here between the subplots. And then we are going to plot 9 maps. This line adds the coastline, so the black line, coastline. Then we add the grid lines, so the longitude and latitude. We remove the labels on the top and on the right. You can see here we have no labels. We add the landmass, so that refers to that. We set the extent of the map, and that's it for the characteristics. Then we're going to plot the data. So we select the first date that we want. And we also define a variable that is step arrows, and this variable reduces the number of arrows that will be plotted so that the maps are easier to read. So then we have a loop on the dates. We define the date of the figure. In this line, we are plotting the wind speed in the background. The wind speed is stored in the netcdf variable wind speed. We select the time in the netcdf file. We select the time that refers to the date we have chosen. You can change here the values of the color bar. So here it goes from 4 to 13. You can change these values if you want. And you can also change the color map that you want. So here it's red, but you can choose any other color map you want. So that is for the background, the wind speed in the background. Now we're going to plot the direction arrows. We're going to use the quiver function and the variables eastward wind and northward wind. Again, we select the time that refers to the date we have chosen. And here you can see that we take 1 in 5 arrows to reduce again the number of arrows. Then we add the title to each map, so the date. Finally, we add the global title to the figure, and we add the color bar, and finally we save the figure. So this is how we built this figure, and now we're going to analyze it. We can see that over these 3 days, the wind speed strongly increased and then decreased over the next days. We can also see that the wind blows from north to south, so alongside the Mauritanian coast here. And therefore, we are very likely to observe an upwelling event over this region and over this period. The first exercise I'm going to propose to you is to reproduce this figure, but using other parameters such as sea surface temperature, nutrients, and chlorophyll, for example. And so you should change here the background color and try to visualize the maps of the other parameters. So we'll now plot our second figure. And these are time series. So we're going to see how the parameters are correlated. And therefore, we're going to plot the time series of temperature, nitrate, chlorophyll, and wind as well. So the first step for this figure will be to define the coordinates of the point on which to plot the time series. So we define the longitude, latitude, and depth. We're taking the depth at 0 so that we observe the surface parameters. And then we're going to select the closest data from this product to this point. So we're going again to use the cell function. And therefore we have 3 parameters. We have the SST at this point, the biogeochemical model at this point, and finally the wind at this point. So again, before analyzing the figure, I'm going to show you how it's constructed. So we have the 4 time series. We have the dates on the bottom of the figure. We have a mini-map here that shows the location of the point that we have defined, and here we have the title that shows the coordinates of the point. This first block here defines the 3 axes, so the 3 places where we're going to plot the time series. Then this block displays the coordinates on the plot, so this is the title of the figure. Then we plot the wind, so we set its title, we put a grid so that we have the lines here. We put the units, on the Y here axis. And then we plot the wind with the function plot. We set the Y limits, and then we remove the dates from the bottom of this time series, so that we only have one axis where the dates are displayed. So we do the same. So this was for the wind, but we do the same for SST, nitrate, and chlorophyll. And then finally, this last box displays the location of the point we're studying, and that's it. So now we're going to analyze this second figure. We are seeing on the first figure that the wind increased on the 8th of June, and this is what we had observed here. So we can see that the wind increased. Then we can see that the temperature decreased, and that's because, as we have explained before, the water from the ocean, the ocean from the deep water rose to the surface, and this water was colder. This water also brought nitrate, and so we can see that the nitrate increased. And finally, as a result of the nitrate increase, we can see that the chlorophyll increased as well with a certain delay, but as a reaction of the nutrients, phytoplankton arrived. So this figure explains very well how the 4 parameters are correlated. The wind chases away the water from the surface, and then the deep cold water rises to the surface. It brings nutrients, and these nutrients bring chlorophyll. Well, phytoplankton that we see from chlorophyll. the second exercise I'm proposing here in this notebook is to change the location of the point. So here you can change the coordinates and see how, if you observe the same correlation between parameters in another place. Our third figure will be to observe the parameters through a vertical section. So we're going to define a section here, so a line, and we're going to see how the parameters along this line have evolved. So here we define the coordinates of the line. So it's the same latitude. The latitude remains the same, but the longitude will vary from minus 18 to minus 16. And we select the depth. The maximum depth will be 100 meters. Just like we did for the point, we're going to interpolate the products along this line. So we use again the method cell, and we select the longitude that refer to that are between the min and max longitude that we have defined. We select data that are at the latitude that we have defined too, and the depth from 0 to 100. We do this for the physical and biogeochemical model. This cell displays the location of our line. So you can see here that it's located along the Mauritanian coast. And we're going to plot now the evolution, as I've said, of the vertical slices over several days. And we're going to see how the parameters are correlated, not only on the surface, on the ocean surface, but also in the deep ocean. I'm going to run the cell because I don't think I had done it. Yes. So you can see here that the cell did not display any figure, and that is because of the last line where we close the fig so that it doesn't appear. That's because we've generated several figures and that refer to several dates. And instead of seeing one figure at a time, we're going to display them as an animation. And this is how we're going to do it. So first we have to import several modules. You can see here that we have named our figures vertical slices date. So we're going to look for all the figures in the out folder that are named vertical slices, because yes, we've also saved them in the out folder. You can no, it's not the right one here. You can see that in the out directory we have generated several figures. So we look for all the figures in this directory that are named vertical slices. We put them in a list. Then we create the GIF, and then we visualize it. So now let's have a quick look on how we built this figure. It's almost the same as what we did before. We have used the P-color function. We're using the longitude and depth variables. This is the temperature, nitrate, and chlorophyll parameters, and that's it, I think. So for the analysis of this figure, this animation, I'm going to plot it again so that we see the evolution, because we have defined 10 loops. Okay, let's look at it from this, for example. So how does it evolve? We can see here that the surface water has decreased and then increased again. We can see here we're from the 6th of June. We also see that the nutrient is rising to the surface on the same dates, and we can see very clearly that the chlorophyll increased after the upwelling. So again, it means that some phytoplankton developed from this upwelling event. Our last figure will be sorry, I forgot. Here's an exercise, the same as almost the same as the previous one. You can change, if you want, the coordinates of the lines. So here you can change the latitude and longitude, for example, to see if you observe the same thing in another region. So, as I said, our last figure will be to plot Hofmöller diagram. Hofmöller diagrams are, they present here, they show the evolution of one parameter. So here the temperature, for example, in one point, so over time, and we see the depth. So the color refers to the temperature, and we can see how it evolves. So again, to plot this figure, it's almost the same as for the other ones, except that the axis will be time and depth. And we are again using the p-color function, and then we plot the temperature, the nitrate, and the chlorophyll. And so for the analysis of the figure, we can see very clearly that the temperature decreased. So at this point, we can see that the water from the deep ocean rose to the surface. We can see that as well as the cold water, the nitrate also rose to the surface, and we see very clearly that from this date the chlorophyll increased, and so this is the result of the upwelling. We have proved and we have observed that the upwelling actually created phytoplankton. And so, as I've said before, the phytoplankton are the very base of the food chain, and this is why on the upwelling regions we have very intense fishing activities. So here's a website that refers the location of every ship in the world. You can we're going to explore it. You can add filters to see fishing ships only. Here, if you select only the fishing ships, you can see that indeed the fishing boats are there are many fish boats around this region, and now you know that it's because that it's an upwelling region. So thank you very much for watching this video. I hope you enjoyed it. And if you're interested in cyclones or river discharge, there is also 2 exercises that explain these phenomena, and so you can have a look at them and study these topics. Thank you again for watching. I hope I will see you in the other videos. Bye.